Have you ever looked up at the night sky and questioned the nature of reality? What if I told you that everything we see, touch, and experience might be a projection of information stored on a distant two-dimensional surface? This mind-bending idea is the essence of the holographic principle, a theory that challenges our fundamental understanding of the universe. Imagine our universe as a grand cosmic movie. The three-dimensional world we perceive is like the image projected onto a screen, but in this cosmic cinema, the screen itself is two-dimensional, a distant boundary that holds all the information needed to create the illusion of depth and reality. This is not just a philosophical thought experiment. Theoretical physicists have been grappling with the holographic principle for decades, trying to reconcile it with our current understanding of the cosmos. Join me as we delve into this fascinating concept, exploring the science, the skepticism, and the profound implications if our universe is indeed a hologram. The holographic principle suggests our three-dimensional universe is a holographic projection of information encoded on a distant two-dimensional surface. Think of a hologram, a two-dimensional object that creates the illusion of three-dimensional depth. The principle suggests the universe operates similarly. This idea might seem absurd at first glance. How can our vast universe be a mere projection of something flat? The answer lies in the nature of information and its relationship to space-time. The holographic principle emerged from the study of black holes, those enigmatic objects in space where gravity is so strong that nothing, not even light, can escape. Black holes presented physicists with a paradox. According to classical physics, information that falls into a black hole is lost forever. This contradicted a fundamental principle of quantum mechanics, which states that information cannot be destroyed. In the 1970s, physicist Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation. This radiation, however, seemed to be random, and carried no information about the objects that had fallen into the black hole. This intensified the information paradox. Where did the information go? Dutch physicist Gerard T. Hooft made a groundbreaking proposal. He suggested that the information swallowed by a black hole is not lost but rather encoded on the event horizon, the point of no return beyond which escape is impossible. This idea, further developed by Leonard Susskind, formed the foundation of the holographic principle. The holographic principle, initially applied to black holes, was soon extended to the entire universe. If the information content of a black hole is encoded on its two-dimensional event horizon, could the same be true for the universe as a whole? This is where the concept of a cosmological horizon comes in. Similar to a black hole's event horizon, the cosmological horizon is the boundary beyond which light from the early universe has not had time to reach us. It represents the limit of our observable universe. Just as the information about a black hole's interior is thought to be encoded on its event horizon, the holographic principle suggests that the information content of our entire universe might be encoded on this distant cosmological horizon. This implies that our three-dimensional reality could be a holographic projection of this two-dimensional surface. This idea is mind-boggling. It challenges our intuitive understanding of the universe and raises profound questions about the nature of reality itself. Is everything we see and experience just an illusion, a projection of information stored on a distant surface? Section 5. The world as a hologram. Understanding the implications. If the holographic principle is correct, what does it mean for our understanding of the universe and ourselves? Our perception of space and time might be illusory. Our three-dimensional experience could be a consequence of information processed on the cosmological horizon. The universe might be far less real than we perceive. Reality as a holographic projection suggests the universe's building blocks are bits of information. This challenges our understanding of physics and existence. Section 6. Supporting evidence, glimmers from the quantum realm. The holographic principle might hold the key to unlocking some of the universe's deepest secrets. Quantum gravity aims to unify Einstein's theory of general relativity with quantum mechanics. String theory, a leading candidate for quantum gravity, connects to the holographic principle. It posits that the universe's fundamental building blocks are tiny, vibrating strings. In the late 1990s, Juan Maldacena discovered the ADS-CFT correspondence. This duality shows how a gravitational theory in one dimension can be equivalent to a non-gravitational theory in lower dimensions. Section 7. Skepticism and challenges, a healthy dose of doubt. Despite the intriguing connections to string theory and quantum gravity, the holographic principle remains a highly speculative idea. Many physicists remain skeptical, pointing out that the theory is still in its infancy and lacks definitive experimental evidence. One of the main challenges is that the holographic principle requires a complete theory of quantum gravity, which we currently lack. Without a full understanding of how gravity behaves at the quantum level, it is difficult to say with certainty whether the holographic principle is a fundamental principle of nature or just a mathematical curiosity. Another challenge is that the holographic principle, in its current form, applies primarily to highly idealized spacetimes like anti-de Sitter space, which is negatively curved unlike our own universe, which is thought to be flat or slightly positively curved. Extending the holographic principle to more realistic spacetimes like our own remains a major challenge for theoretical physicists. Despite these challenges, the holographic principle continues to captivate the imagination of physicists and the public alike. It offers a tantalizing glimpse into a reality that might be far stranger and more wondrous than we ever imagined. Section 8. A universe of pixels? Exploring the analogies. To grasp the concept of a holographic universe, it's helpful to rely on analogies. Imagine a computer screen displaying a three-dimensional image. The image appears to have depth but is composed of tiny, flat pixels. Similarly, our reality might be a projection of information on a two-dimensional surface. Another analogy is a hologram, created by recording light wave patterns. When illuminated, it recreates a three-dimensional image. The universe might operate similarly, with our reality encoded on a distant surface. Section 9. The illusion of depth, our 3D experience in a 2D universe. If our universe is a hologram, how does our brain perceive depth and three-dimensionality? Our brains are wired to interpret visual cues such as perspective, shading, and motion parallax to construct a three-dimensional representation of the world around us. These cues trick our brains into perceiving depth, even when viewing a flat image. In a holographic universe, these visual cues might be manifestations of the underlying two-dimensional information being projected onto our three-dimensional experience. Our brains, accustomed to interpreting these cues in a three-dimensional world, would continue to perceive depth and volume, even though the information itself resides on a two-dimensional surface. Think about watching a three-dimensional movie. The movie itself is a two-dimensional projection, but by manipulating light and creating specific visual cues, it tricks our brains into perceiving depth and three-dimensional effects. Similarly, the holographic universe might be tricking our brains into perceiving a three-dimensional reality from a two-dimensional source of information. Section 10. Redefining reality, the philosophical implications. The holographic principle, if true, has profound philosophical implications, challenging our understanding of reality, consciousness, and even free will. If our universe is a projection of information, what does it mean for our sense of self and free will? Are we merely characters in a cosmic play, our actions predetermined by the information encoded on the cosmological horizon? Some philosophers argue that the holographic principle supports the idea of a simulated universe. If reality is ultimately information, it suggests that our universe could be a sophisticated simulation running on a cosmic computer. This raises further questions about the nature of the simulators and their motivations. Others argue that the holographic principle points to a deeper level of reality beyond our current understanding. If information is fundamental, it suggests that consciousness and reality might be more interconnected than we realize. This has led some to speculate that consciousness itself might play a role in shaping the holographic universe. Section 11. The quest continues, unraveling the mysteries of the cosmos. The holographic principle stands as a testament to the boundless capacity of the human mind to explore the universe's mysteries. While it remains a theoretical concept, it has sparked a revolution in our understanding of space, time, and the nature of reality itself. The quest to understand the holographic universe is far from over. Physicists continue to grapple with its implications, seeking experimental evidence to support or refute its claims. New theoretical frameworks are being developed to test its limits and explore its connections to other areas of physics. such as quantum information theory and cosmology. As we delve deeper into the quantum realm and probe the universe's furthest reaches, we may one day uncover the truth behind the holographic principle. Whether our universe is a hologram or not, the journey of exploration and discovery will undoubtedly lead to profound insights into the nature of reality and our place within it.